income prepaid telecommunications. And we are awarding him this recognition for his work as a founder of an organization called Data Science Nigeria that stimulates the data science ecosystem in Nigeria and in Africa. I will let him tell us more about the Data Science Nigeria initiative, so give a round of applause to Bayo Adekanmbi.
Thank you very much. Thank you very much. Thank you very much. Thank you. Thank you.
Do you want me to get this?
Okay, thank you. Okay. Thank you very much. This is to Africa, to the continent, to the great work that all of us are doing. And this is to the team from Nigeria for supporting this great dream. It's a great pleasure for me to join Indaba this year to celebrate what we're doing in Nigeria and to provide some references in terms of best practices, while we also learn from everyone on how to scale up and build a very high impact AI ecosystem on a sustainable basis. Now, one common denominator that I've seen at this session that's been repeated by all the speakers is the fact that Africa is the future of AI, which validates the fact that we're just doing the right thing as we build a big community. But one thing that we observe over time is that we get blinded from our progress because of our myopic obsession with our problems. But everyone that has spoken kept saying our problem is our biggest advantage. So I'm very excited that we're doing the right thing, and as we continue on that trajectory, we're going to put Africa in the forefront of AI. But to amplify the voice and taking these to our various local areas and sustain the momentum, which is the theme of this program, amplifying the voice, there's a need to understand that it's beyond great events like this, because great events do not make great people, these great decisions. How do we take this to our various campuses and community, amplify to, reverberate the sound and get the message even to our various corners? And that is why what I'll be talking about this morning about Data Science Nigeria will be useful in terms of some of the things we have done in building the community. So these are some of our key numbers in terms of what we've done, but I'll speak to this very speedily. So to make the presentations a little bit more African, I'm going to use a lot of African proverbs to capture what we've done, and a lot of images, so the slide will be very, very fast to capture the story. So the first thing is the fact that a hunter who has only one arrow does not shoot with careless aim, which means that in building a high-impact community, there must be a sense of vision. You must have clarity about your point of arrival. There must be certain indicators that give you an indication that there are certain things we are running after. Because even though community may evolve naturally, but we've come to realize that we cannot build a high-impact community in a very haphazard way. There must be a sense of clarity. What is it that we want to achieve? What are the key measures of our success? And can we scope or scale it to time such that we can galvanize all effort towards that? Because if there is no sense of a point of arrival, it's difficult to galvanize effort towards a direction. And that was why the first thing I will share is the fact that there was a clear vision. And the vision was big, audacious, which is to raise 1 million AI talents in Africa, with Nigeria being, a base. And why do we do that? There are two critical levers that drove that. Number one, we need to make our population count. A country of 200 million people, growing at 2.3% annual growth rate, which means in 10 years, our country is going to be 234 million people. That is more than 7 European countries added together. And if you look at the fact that out of that, 150 million will be under the age of 25. So the quick question is, how do we scale them up with the right skill that can be useful to the nation? The second thing has to do with our GDP, which is the measure of our national productivity. And the game is, what are the key sectors of the economy that are driving growth? So how do we engineer a process where AI can be embedded by building talent? So therefore, for us, Data Science Nigeria is a strategic intervention to retool and reskill a nation for sustainable economic development and for building global competitiveness. And that was why the vision was set around key parameters of national growth. So, and of course, the vision was scaled into 3 years, 5 years, 10 years, and is driven by talent access, enrichment, and deployment. The second proverb that we drop for us today is the fact that knowledge is like a lion. It cannot be gently embraced, which means if you want great impact, you must be disruptive, diversified, and somewhat aggressive. And that informs our model. Our model is based on 2 parameters. Number 1, we wanted to understand the segment that we must affect if truly we want to build an ecosystem that can have socio-economic impact. So we're able to scale that to various segments, beginners, kids, and teens. Like I said, if we're going to have 1 million people in 10 years, we have to look at the population of Nigeria. Median age is 17.9 years. So which means we have to start scaling up from young kids, teenagers, intermediates and experts, university students, and more importantly, professionals, C-level, and government. Because it's important that while we're building talent supply, there's also talent demand. And then, beyond the segmentation, was also the channel of engagement. What do we want to use? We were clear on using face-to-face, using online, offline, and hands-on. So based on these 2x2 matrices, we're able to build our propositions, our platform, and our products to serve various set of people in achieving our clearly marked vision that is galvanizing and driving our effort. Okay, so I'm going to run through a lot of them very speedily in terms of our face-to-face. Our biggest face-to-face is what we call AI Everyday, where we run AI classes for all kinds of people from Monday to Saturday. I have some of our instructors who are also seated there. And this is for different classes of people based on their level. And these are how classes run. And all these classes run free of charge, to mobilize different sort of people. Whether you are a teenager, you're in secondary school, that's high school, or university, or pre-university. And then beyond this location was the opportunity to take AI learning to 30 cities in Nigeria, to get as many people as possible to be exposed to possibilities of AI. So this took us to 30 states, and thousands of students got the opportunity of learning AI in a dynamic way. And of course, we have a dedicated AI hub where people can go anytime to read, study, meet people, have access to tools for research, access to library, and also meet people and grow as a community. And then we extended to campus where we built AI plus clubs on campuses where people can network, learn, share best practices, and deepen the community. And then we saw the need to scale up at industry level. So we started a program for professionals, middle-level professionals in banking, in finance, in oil and gas, in telecoms, to be able to deepen the impact, And then our ultimate AI bootcamp. Our AI bootcamp runs once in a year and is the peak of the pack. Why? After we've done all the AI everyday, AI invasion and all that, this is where everybody look forward to. So we run 100 days of study, a cargo competition, and then we pick the best 200 students that make it to the boot camp, which has become, a place of pride for anyone who makes it there. Of course, we do that through what we call inter-campus machine learning competition for universities. Last year, we had over 10,000 students who participated, and we're building the momentum. What this does, it allows the student to learn the skills of the future in complementing what they are learning in school. So this is how the boot camp looks like. Some of the faces you have seen at the events are also the kind of speakers you see there. And also we give best student scholarship. This year, scholarships to Stellenbosch, MSc in artificial intelligence. And then we run classes for executives. I'm talking about directors of companies who make decisions on how much money they're going to invest in talent building and community development. So here we demystify AI for them in the language of business such that they understand how it drives revenue, cost reduction, and business efficiency. And of course, we run a lot of engagement programs and summits every year, bringing together academia, government, industry leaders to situate and demonstrate how AI can be a catalyst for socioeconomic development in a practical way. Okay, these are all government-related engagement that we have done demonstrating AI, big data. Now, the next thing is the young bird does not crow until it hears the old one. So we must proactively build capacity for digital native. So we've done a lot for young people. So we run a lot of classes for them, building their skill set in coding, Python, machine learning, and basic robotics. In addition to that, they are learning, but you also get them on a global platform. They go to Kaggle, even though they're 12 years, 13 years, 14 years. The financial inclusion project on Zindi, a lot of our 12 years, 13 years are all on Kaggle working on it because the quality must be benchmarked against global standard. The fact that you are in a village in Nigeria does not mean you are less than anyone in the world, since we have an equalizer platform like Kaggle where they can all practice, submit their codes. And then we do online classes. We run 100 days of machine learning that has seen over 300,000 views across the world. And our focus is a lot on the mathematics of machine learning to scale up people. Now, you learn to cut down trees by cutting them down. I guess you will agree with me. So the intention here is, guys, we must put our hands in the groove. So here, Kaggle and Zindi for us is a practical way of demonstrating your theoretical learning. So we are so focused on driving this thing to the extent that in Kaggle, in Africa, we have run more Kaggle competition than any group on the continent. Even Kaggle recognizes that because that is the only way you can benchmark yourself. Of course, on Kaggle ranking, guys in our community are some of the leaders, and myself, I'm a solid Kaggler, access to global data and compete and prove to the world that we're doing some serious things in Nigeria. Okay, and then we rely a lot on mentors, experts all over the world who support our student growth. And then we run master classes where experts in the world dial in on a regular basis to teach offline content. We democratize learning through our AI knowledge box to address the problem of internet and power in Nigeria by downloading all open courseware on AI from all top schools in the world, MIT, Oxford, CMU, Stanford, and put them curated by levels into this 2 terabyte USB of over 10,000 videos and includes all conferences, Indaba, because not everyone can go to the internet and watch. Now, students can pick this and do it. I was told about a student who got this, and for 36 hours, the student was watching the videos. That's the level of passion that is. So this for us was a game changer in democratizing knowledge and making things available to all people. In addition to that, we've written books. One of our biggest books, which have seen over 500,000 downloads, with someone like Joshua Bengio also contributing to it, which are validators of our global benchmarking and quest for global standard. And of course, our biggest game changer is this book that will be released November 19, which is introducing Python and machine learning with local nuances for grade 5 to 9. You remember our vision in 10 years. So we must start from secondary school and raise talent proactively and deliberately. So this is a game changer for us in Nigeria. The strength of the crocodile is in the water. Everywhere else is got no strength. So pipeline building. So what do? We deploy this talent to the industry very, very early. So what we do is we work with industry, give us your company data, and we bring our students to work on your data such that while they are in school, they are already learning the real world of data. Companies like KPMG, Access Bank, our partner, to the extent that today, data science in Nigeria is the biggest talent pipeline for companies in Nigeria and even outside Nigeria. Now, we are the platform that helps companies to recruit data scientists, as you can see. Okay, and we've seen some students from our community winning global awards for what we do. And Zindi, we are one of the biggest ranked on Zindi, and we're so proud of that, and we'll continue to do that. Next, a single stick may smoke, but it will not burn. That's Ethiopian. So we must collaborate, partner, build. Of course, we are proactively driving community. We're co-host and sponsor of Indaba X in Nigeria, partnership with different platforms, organizations, Data Science Africa, AIMS, UN Pulse Lab, fraternizing for best practices, knowledge exchange, idea generation. Okay, looking after a pregnancy is not difficult. It's much more difficult to bring up a child. That is Swahili. So what does that mean? It's great to have great ideas, but scaling up sustainability and structure, for me, is the game changer. That's what we've done in Nigeria now, where we have structured advisory board as a registered nonprofit, which means we are accountable, and the fact that we publish our annual report for financial audit, and the fact that we are now doing projects that are bringing revenue for us, even as a nonprofit. For example, we built a financial inclusion lab for our country, and we're so proud of that. And there's so many other projects we're doing for the country, which means AI is not just a meet-up by the corner, but it's becoming an integral core of national discourse by the reason of the outcome and output that we have created in our community. Okay, and by doing this, we generate sufficient revenue to scale up, and more importantly, to be able to sponsor students to this kind of event, sponsor them to international event, get them to do masters and all that. That is one thing we are so passionate about. And then we're doing a lot on AI for good. Some of our projects, AI Class Monitor, to address a problem of overcrowding in our classes, AI Class Monitor, that is that. Nalai, to address issue of financial inclusion. And then we went into data. I've seen a lot of projects here. The problem has been local data. So what we have done is to proactively develop crowdsourcing apps that can allow us to collect all types of data from every part of Nigeria, whether it's voice, whether it's image, whether it's video. So we built Marketel and Check For Me, and we're going for the third one in the next few days, such that every single data, we can have access to it. So ladies and gentlemen, I'm excited about the opportunity that Indaba provides, and today, we've been able to build 24 unique engagement platforms for different classes of people serving different purposes. In addition to the fact that we have now moved into the advisory board for the government. Just last Friday, we led a session with National Economic Summit Group, the largest think tank for the country, to be able to demonstrate how machine learning can be used to map our national inclusive goal. I believe that's the only way this narrative becomes compelling, when it begins to change, begin to drive national policy, and more importantly, drive for evidence-based policy advocacy. You can download our annual report on this platform to see what we do. This is about 100 pages document capturing what we do based on the skill that I've explained. So, in conclusion, ladies and gentlemen, I go to Sudan, my last proverb for today. We desire to bequeath two things to our children. That's what Sudanese say. The first one is roots, and the other one is wings. One of the things that come through at this session is that root. We are Africans. We have a problem, but we can solve it. Sense of identity, sense of our voice. The second thing is the wings. What is the wing? After this program is the need for each of us to fly and carry as many people as possible in our various community to know and be able to express this reality that we have seen at this event. Like Winston Churchill says, we make a living by what we get, but we make a life by what we give. So the mandate on us is to rise. Africa is waiting on us. Let's go make it happen. It's beyond the nice atmospheric of deep learning in Indaba. It's what you do when you go back. Let the cycle of benevolence continue. The guys who have put this event together have invested so much, the sponsors. The best we can do is to go back and do much more. As a round off, I want to acknowledge people who have supported this dream. Black in AI, Deep Learning Indaba, Government of Nigeria, friends, our sponsors, our partners, and many layers of volunteers who have been part. But I must not forget to mention my wife, and I will explain why, who in 2016, November, after I came back from my PhD research, said, young man, now you are at the peak of your career, you have a PhD, what are you going to do to add to the community? And then we started Data Science Nigeria, November 2016. And she did it by taking a bunch of our family investment and say, we're going to put this money into driving data science. Today, she stopped her work and she now gives all her time to support Data Science Nigeria administration on a full-time basis. With her, so many other volunteers. It's great to have great women who support great vision. So, ladies and gentlemen, it's a pleasure to be here this morning. I hope this will inspire someone to go back and let the voice be heard. And let the voice be heard, Africa arise. Thank you very much. Thank you. Thank you. Okay, no question.
If you have any question for Bayo, please ask them now.
Okay. For me, I think the narrative is you got to prove yourself. You got to prove yourself. we put together a national growth agenda that government saw, and they got interested. Nobody responds to sentiment. People respond to purpose and impact. So it became easier for government to say, guys, come drive our inclusive growth modeling, macroeconomic modeling. So what I would advise is, as we scale up and build talent, let's channel those talents to solving local problems. Let's channel them towards solving local problems. And I think that's some of the things we had yesterday, even from Andrew. We can't play catch-up. We can't be like Western technology companies, but we can look inward and ask questions. Financial inclusion, agriculture, health, all the infrastructural deficits that are peculiar to our continent. How can we use AI to solve them? As soon as you're doing that in your corner, I tell you someone will see you. And that is our story. When we started publishing stuff and they're seeing what we're doing, they naturally look for us. And that for me is the story. Okay. Any other question? Okay. Thank you very much.
I don't know about you, but I'm fully energized right now. Bayo really embodies what the Maathai Award stands for, so please give him another round of applause. We are a little bit ahead of time. It is my pleasure to introduce our keynote speaker for the morning, Dr. Richard Socher. Is he here? Oh, great. He is the chief scientist at Salesforce, and he was previously an adjunct professor in the CS department at Stanford, and also the founder and CEO of a startup called MetaMind that was acquired by Salesforce. And if you are into NLP, you probably also know him through his excellent course. Bear with me 1 second.
All right. I am on.
Great. I think we are almost ready to go.
All right.
Yeah, like I said, he was the CEO of a startup that was acquired by Salesforce called MetaMind, and he's now chief scientist at Salesforce. He's going to tell us about multitask learning. So please help me welcome Dr. Socher to the stage.
Thank you. Thank you. Aloha, everybody. I'm super excited to be here. Just arrived last night and look forward to meeting all of you later today. So I want to talk to you about one of the things that I think is probably one of the biggest open problems in artificial intelligence, and that is multitask learning. And the way we're motivated to work on this research is that we looked into the last couple of years since AI has kind of taken off like crazy. It's been around for a long time, of course, but in the last couple of years, we've seen a lot of step changes in AI. By the way, if you have any questions, just raise your hand, and I'd be happy to take any questions at any time. And what we've noticed, and what I think we can kind of categorize these different stages as, was that for a long time, machine learning was essentially largely dependent on feature engineering, where if you wanted to do sentiment analysis, for instance, in natural language processing, you may have people that say, here are a bunch of positive words like great, wonderful, amazing, beautiful, and so on, and here are a bunch of negative words like lame and boring and stupid and whatnot. And then you'd say, well, if we just kind of use a machine learning algorithm to assign weights to those words, then we probably do reasonably well. And you get maybe 60% accuracy already, just because once you say the word awesome in a sentence, very likely that's a positive sentence. And then you look at your errors and you realize, well, there's negation too, so maybe we create a feature that said not one of the lists of positive words, and that gets assigned a weight through machine learning, and so on. And you realize, well, but there are some ways where you say not so really amazing, and then you have multiple words, and you create regular expressions, and so on. So we can go on for a long time. But that is kind of where the field of natural language processing was up until maybe even 10 years ago, mostly at. And so deep learning in 2010 or so started to change that a lot, in that we switched the thinking from we have human experts that assign and define all these features to we have a deep learning system that takes in as much raw data as possible. Here's just a list of words and define the label you want to predict. And that, I think, was a big step change. What we're currently in is a lot of deep architecture engineering, where we look at each specific task and we see, okay, how can we architect the model such that it'll be good for this task? And that has obviously been a huge success for many, many different tasks: computer vision, natural language processing, speech recognition, and then inside each of these fields, like image segmentation for computer vision versus object detection. They're all deep learning models of some kind now, but they still have a lot of human skills and development for each particular task that are required. And we see this especially in natural language processing, because NLP kind of captures almost everything else in AI, if I may say so. Because in the end, language needs to communicate about the visual world, about the logical world, social world, and so on. And so the question is, okay, we can probably squeeze out another couple of years of deep architecture engineering for each particular task. But what's next? How can we progress further to maybe go to even more general AI systems that in the end don't have to be tuned for every single task, but they can just continuously learn in the future? And that is kind of one of the motivations towards what I'll talk to you about. Another one is just looking at how far we've gotten with single task learning. And this, I think, is kind of where we are at the community, as a community right now, similar to this dog. And that we can get pretty good performance. We can go a certain distance as long as we have a very specific data set and a very specific task definition. Then we'll do our model architecture engineering, and we try to hill climb on a metric. And as long as the data set is roughly the size of and representative number of examples of 1,000 times the number of classes, then my hypothesis is deep learning will get you close enough to run something in production, maybe 90% accuracy or F1 or something like that. And it's also clear to me that if we want more general AI systems, we need to have more continuous learning of a single model, that we say, oh, you know these things, here's a new task. And you should start doing well on that too if I teach you a little bit of that task. You shouldn't have to restart from scratch every time you hit a maximum limit of some performance. And the first inkling of that being the right idea is, I think, what we see with pre-trained models. So in pre-trained models, of course, in computer vision, we've seen this being a huge success. We know that a ImageNet pre-trained convolutional neural network is probably the best place to start for any computer vision problem that you may have. And in computer vision, in some ways, everybody very quickly rallied around this idea that, yeah, sure, we should have not just the first layer pre-trained, but maybe 20 layers of a ResNet be pre-trained. And partly that was because in computer vision, everybody rallied around this one classification task. And it's very easy to say, well, if you can't even distinguish a cat from a dog or something, then why try to do full scene segmentation and scene understanding or something like that? We've seen a little bit of this also in natural language processing with word vectors. Word vectors starting with word2vec and glove, sort of single representations. Then we move to contextual vectors. And in my NLP talk in a little bit, I'll go into some more details on this. And now we have even more powerful contextual vector representations like Elmo and BERT. And we've had some success representing words and using a pre-trained word representation to start our deep learning models. And just a show of hands so I don't sort of talk past the audience, can you raise your hand if you're familiar with BERT? All right, cool. All right, so roughly 2/3 of the audience. For the other third that is interested in it and doesn't know it, in about an hour or so after this one, I'll talk about more details on word representations. But the main idea is that basically you look at the context of each word, and then you look at the statistics of how often does that word appear in the context of other words. And then it turns out that walking, for instance, appears in similar contexts to running and going and moving and things like that. And so now you have a list of numbers, a vector, that basically tells you that walking and running are more similar to each other than walking is to sleeping, which appears in different contexts with like bed and night and so on. All right, so in NLP though, unlike in computer vision, there wasn't a single task that the entire NLP community agrees on, that if you do really well on this task, you've clearly made a huge amount of progress in NLP. Because the sentiment analysis community has quite different models to the translation community, to the parsing community, and so on. And there are certain models that win in parsing that nobody in their right mind could use for machine translation just because the data sets in MT and translation are much, much larger and need to be much, much faster. All right, so the question then becomes, why has weight and model sharing not happen as much in natural language processing as it has in computer vision? We're really, for the most part, we just switch the softmax at the top, and then we can use the same model for lots of different kinds of things, mostly CNNs. So I already briefly alluded to this, but in NLP we have all these different types of reasoning. Sometimes you can have a sentence where you say, 3 people were in the room, 2 people came in, how many people are in the room? And now language is all of a sudden a math problem. And very simple one, but one nonetheless. And sometimes you say, this is a typical Nicolas Cage movie, and that probably means it wasn't a good movie. And no offense, hopefully he's probably not in the audience. That's okay. So we have all these different kinds of reasoning. Emotional, sometimes we can talk about the visual world, and we reason visually, and language kind of connects all of these other areas of AI. And in some cases you might say, imagine time travel was possible, and then you say something else. And now you have these hypotheses and these different worlds, and you need to keep some of it in your short-term memory and other things in the long-term memory and so on. And I think partly because NLP is so hard, the community has kind of subdivided itself into all these different intermediate and separate tasks, and then has, in some ways, been sort of benchmark chasing in each task separately. And you might now say, okay, well, I get single task learning maybe has some limitations. There are some folks now who say, well, the future is actually unsupervised. It has to all be unsupervised. But I think that's clearly not the case for language. If you put a child by itself in the jungle, they'll probably learn a reasonable visual system to identify different kinds of objects, things that might eat them and whatnot. But if a child lives by itself, it will not learn actual language. So at the very least, it has to be multiple children, and then they might actually develop a language. So there can be some kinds of community self-supervision type situations if you have enough grounding and other things. But for the most part, for most people, language clearly requires a lot of supervision in nature, and I think for our models as well. And so that kind of led all of these different things, sort of where's the community going, how has pre-training helped, and so on. All of that led us to this idea of trying to find a unified single model for NLP that essentially can have everything pre-trained. Not just the word vector layer, not just maybe now contextual word vector layers, but everything including the output layer, the decoder. And if we're able to do that, then we can just have that model get smarter and smarter over time. And I don't want to talk too much about sort of AGI and these super general AI systems, but it's fairly clear to me that if you ever were to try to get to that in the future, whatever that system is needs to have the ability to learn multiple things at once and not restart at every task from scratch or from some small intermediate representation. More sort of concretely and realistically in our timeframes and lifetimes, when we have this, if we get to this unified multitask model, we can more easily adapt to new tasks, and I'll show concrete experiments for that. We can make deploying systems to production much, much easier. Right now, and we have this same problem in Salesforce, but I think most every other company has it too. You have a machine translation team, and you have a sentiment analysis team for social media, and you have a team that tries to understand natural language questions for an FAQ lookup, and you have another team that works on chatbots, and so on. So you have these different teams, and they all have different models, and then trying to get those models running on a very large scale for a large internet company requires time and work, and a lot of people each time. If you had a single model, then you at least wouldn't have to have different modeling experts for all these different tasks. Also, just like in computer vision, where you can now download a ResNet, a couple of weeks ago I talked to this high schooler, he's like in 9th grade, and he's like, so why do you think ResNet is good, and should I be using ResNet? I'm like, man, when I was in 9th grade, I did not know about anything machine learning, but it's also incredible because like when I dug in a little bit, he's like, yeah, how did you implement it, and so on, and really just like, what he had to do was put 1,000 pictures of something in one folder, a couple hundred pictures in another folder, and then he ran sort of a standardized code, which, still very impressive, still not what I was doing in 9th grade, but, he didn't have to like really go in and modularize everything and build a bunch of crazy PyTorch code. But it has shown us that we basically have commodified computer vision enough where it's just like, here's some building blocks, do something new, something that nobody's ever done before. Maybe you just have like a water gun attached to a webcam, and whenever a squirrel tries to eat your fruit, the water gun shoots water and distracts the squirrel. Like those are real applications that people can now build. Not the most impactful ones, obviously. We work in computer vision for medical applications, which are much more powerful. But it shows us that there are a lot of things that you can do now very quickly, and that is because the bar has been lowered through these commoditized and generalized models. And the hope is that even now we can, with this model that I'll describe to you, move towards continual learning, where we just have a single system, we have new tasks that come in, and they just get smarter, and you don't have to restart and rebuild a whole new model. All right, so hopefully most of us are somewhat on board now with this idea that we want to have a single model. Are there any questions so far about single models? Yeah. I'll repeat the question if I hear it. That is a great question. So the question is, when you have a single model, is the goal to get state-of-the-art on each separate task that are part of it, or we just want to have reasonable performance on all of them? That is a very astute question, and I think is part of why this is not as accepted in the community right now. Because the community right now very much is like, if you want to publish a paper, you better have that SOTA number, that state-of-the-art number on that task. And if you have a single model like this one here that literally can do 10 tasks in one model, but it doesn't get state-of-the-art on like one of them, and the reviewer happens to be mostly in his career optimizing that SOTA number on those data sets for that task, like machine translation, and I'll show you in a second, he'll be like, this model is completely useless, because why would I ever use anything that's not state-of-the-art in my subfield? And so this is actually part of, and the interesting thing is I've seen a lot of this when in 2010 I tried to, and eventually succeeded at publishing the first deep learning papers at a natural language processing conference, where my very first submissions also didn't have state-of-the-art. They were like 0.5% below, but they had zero feature engineering. And people are like, this is useless. Why would I ever use this? It's below state-of-the-art. And I'm like, but I didn't have to do anything. Isn't that amazing? And like, it didn't matter until we actually got state-of-the-art. And then people like, and then I literally had reviewers still who were like, why are you submitting a neural network paper to this conference? This is an NLP conference. Like, this is the stuff we know didn't work in the 90s. I'm like, why didn't you read to the end where we now have state-of-the-art? And then, eventually it worked. And so that's part of it. So to make a long story short, we of course still want to get state-of-the-art on all the things and have as many things as possible. My hunch is I'm personally more excited about a model that can do 10 different tasks and can do zero shot on an unseen task, which we'll show also. So it can do things that it was never trained particularly to do on another data set with 1,000 examples per class, and then we kind of fine tune on that. And instead it just works on a new task it's never seen. I'm much more excited about that than another 0.5% improvement across the board on like 5 different tasks or something for a pre-trained word vector, or another, 5 very specifically tuned model for one task. But the goal is eventually to have all the things, but we're not quite there yet. Great question. Do you have another question? All right. So now the big question for us was, okay, let's say we do want to build this one model for all the different tasks in natural language processing. How should we cast what these models, these different questions that you might have about something linguistically, these different tasks as? And so I think broadly, all of the tasks in NLP can be cast as one of those 3 things that we see here, namely sequence tagging. You have a label for every single word in a sentence, like named entity recognition. Is this a location or a person or an organization, for instance? Or in this sentence, is this particular word positive? Does it have a positive sentiment or not? Like I might say, the screen of the iPhone is great, but I didn't like the photo quality or something like that. So then photo quality is negative and screen is positive in that sentence. So that's aspect-specific sentiment analysis. So that is a broad range of tasks. Then a second one is just general text classification, where we have a single label for an entire sequence of text, like dialogue state tracking or sentiment classification for the entire sentence. And then I think the most interesting group, which also includes the hardest and most challenging tasks, several of which we haven't really solved yet at all, is machine translation, summarization, question answering. And all of these tasks can essentially be cast as a sequence-to-sequence model. You have a sequence of words that comes in, like German words, and you have a sequence of words that comes out, like English words or Swahili words or something like that. And so, and summarization is also, you have a sequence of a longer document, sequence of words comes in, and you want to have a sequence of words that is shorter, truthful, and still includes all the important information. Summarization is actually a really hard task, and I feel like probably the most interesting and challenging task right now if you were to just look at one single task. Because I just, after, we've had a couple of papers now inside the field of summarization, and we're trying to think about, okay, what's the best description of what is actually a good summary, right? And it's really tricky. You might say, well, it has to be shorter, and all the facts in the summary should probably be mentioned in the original document, so they have to be true. But then you can actually say, well, that is definitely not a good enough summary. Like if you have, for instance, A punched B, and that's the summary, then maybe you think, oh, A is a horrible person. But what if B punched A first? And now you're like, oh, maybe they're just defending themselves, right? So like all the facts were true in the summary, but there's still a really bad summary. Or you just say, the sun shined on that day. And now you're like, okay, that's true also, but it's completely irrelevant because, there's some plane crash or something, and it was irrelevant that the sun shined that day. And so summarization, super hard. We'll use it as one of the tasks, and we'll take all of these with a grain of salt on summarization, because even the metrics of how we evaluate summarization are somewhat questionable. But I digress. Let's move on to now thinking about how to cast these different frames that we had here in these different types of tasks into a single mega task, or what I call one of these three equivalent super tasks of natural language processing. And what I mean by that is that basically any of these three, and basically every NLP task, can be cast as one of those three tasks here, namely language modeling, question answering, and dialogue. And if you have any tasks that you feel like could not be cast as one of these, or how these could not be cast as one another, I'd love to hear it. But basically, language modeling is just the very simple task of trying to predict the next word. Language question answering, just you have a document and you have a question about that document and you want to get an answer about it. And so, for instance, if I want to do named entity recognition, which is a sequence tagging problem, I can cast it as question answering, just asking what are the locations, organizations, and people names in this sentence. And then its NER is a question answering problem, also trivially. Dialogue, everything, is essentially when you ask a question, it can be also asked inside a dialogue, but then you could keep on asking questions. And now, what I'm arguing is that essentially dialogue is also similar to language modeling, in the sense that if you have a continuing sequence of multiple back and forths, at each time step in a chatbot system, you would still want to predict the next couple of words to give an answer given the previous sequence. So the sequences just get longer and longer. Likewise for question answering, if you have a dialogue, the content document, the context document can just keep getting longer and longer as the dialogue progresses. And so in some sense, you also can cast dialogue systems as question answering. So basically all of these three tasks are equivalent. The way we currently see them, though, is for a long time, language modeling was just to give us a perplexity, how likely is a given sequence given some kind of conditioning. And so, for instance, if you wanted to know, you had a speech recognition system, and you wanted to know, is this the price of wood, for instance, was the sentence. And now the price of wood, you know from the context that the word wood is probably W-O-O-D, as in the wood that comes from a tree, but in the context of would you want to hear about this model, wood is the W-O-U-L-D. And a language model would tell you simply which wood is more likely given the context in a sequence. And nowadays, we've seen language modeling in a lot of word vectors and a lot of great pre-training models, and I'm very excited about seeing the rest of the community kind of realizing the potential that language modeling has, and we think actually it's even bigger than what we currently see. That being said, some of the tasks right now that are out there, namely question answering and things like that, require much, much longer sequence understanding, and language models currently still don't have the ability to go back 1,000 words into the past and then make a reasonable judgment about them. And so I want to present to you here the 10 different tasks, all of which we defined as question answering tasks. And the general question answering format, you can also think of a sequence times sequence to sequence, or in a way, the task is encoded as a question. And in every one of these examples, you essentially have some kind of context document, you have some kind of question about that context, and you get an answer. So very, very simple. Two sequences go to another sequence. And here are the 10 examples of tasks that we have cast into this. So here, the first one is the standard Stanford question answering dataset, SQUAD, where the answer to a question is always just a subphrase in the document. So if you ask the question, what is a major importance of Southern California in relation to California and the United States, then maybe the answer in that Wikipedia paragraph was it's a major economic center. So a relatively simplified form of question answering. But we can also ask, for instance, what is the translation from English to German of this sentence? And so now machine translation is very simply also another type of question you might ask. We can also ask, what is the summary of this longer context document? And the answer is a shorter sequence that we're trained to be a summary. And you can also think of entailment, a very interesting task in NLP that is pretty broad also, the idea that given two sentences, you always want to know if they're logically entailing each other, if they're contradicting each other, or if you can't make that judgment. And that's very useful, for instance, for summarization, where you might want to say, well, is that summary actually logically entailed in the original story? And if it's not, then probably that's not a good idea, though right now all the entailment data sets are single sentences. And like I said, in summarization, you might have every single sentence be correct and entailed in the original story, but your summary might still not be because you mixed up the timing. And that can be a huge difference if somebody attacked somebody first or afterwards. Makes a big difference in the summary and the truthfulness of it. Another very popular task, sentiment analysis, very simply can be cast as, is the sentence positive or negative? And now what's interesting here and important to notice is that when we ask questions that are similar to classification, we want to make sure that the labels that you see and that you might want to classify this sentence as are actually part of the question. And it's somewhat a simple idea, but it's very important because this way we'll be able to ask questions that we've never seen at training time before. So for instance, we could say, Richard gave a talk and nobody clapped. Is Richard happy or sad? And so even though we've never trained it on here are 1,000 happy stories, here are 1,000 sad stories, but if happy and sad are also in here, and the model eventually learns that it can point to these kinds of words, and in this case here would correctly say, all right, this is a positive sentence, and it learned to do that by also knowing that it can restrict itself to answers that are somewhere in here. And so the color coding that you see here is that across these 10 different tasks, sometimes the answer comes from words in the context, sometimes the answer comes from a standard softmax word classifier, and sometimes the answer comes from words in the question. And there are a couple of others, slightly less popular tasks, like translating natural language English questions to SQL queries. It's actually very useful. There are a lot of people who know about databases, but there are even more people who just want to know something about their business, and they want to know how many cars did we sell in Kenya in the year 2007. And now they don't want to have to go and learn how to program in SQL in their database. They just want to ask that question in natural language and then still get an answer based on the data set that they have. So very important task. Dialogue state tracking, for instance, what is the change in dialogue state when somebody asks, are there any Eritrean restaurants in town? And so the state that was triggered by that question is that this dialogue is now about food, and particularly about Eritrean food. So these are essentially the 10 different tasks, all of which we cast as question answers, questions over some kind of context. So we have also semantic role labeling, relation extraction, dialogue state tracking, semantic parsing, as in this English to SQL translation, and common sense reasoning, which is a pretty broad term for essentially Winograd schemas, where if you have a sentence here like Joanne made sure to thank Susan for all the help she had given, you now want to know which one does she refer to. So in some sense, anaphora resolution is another word for this. Okay, so basically, by casting all of these as question answering problems, we've moved from the standard supervised learning where you as a person or a researcher or programmer define, here are my inputs X, here are the outputs Y I want to predict for those inputs. And instead you're including in your overall model, here's an input X, here's also a task or a question I have about that input X, and now give me an answer given both of those things. And what that enables us to do is that you can now elevate the model to figure out itself how to tune itself for each task and each question that you have, instead of you having to do that externally from the learning loop. We sometimes jokingly called the previous version graduate student ascent. Right? You know, stochastic gradient descent is graduate student ascent where outside the tasks were defined and you just made the model do this. And whenever we've seen less feature engineering, less architecture engineering, I think the better eventually the models will get and the more generalized they get. So again, very simply, we use a question as a natural description of each task T out of these 10 tasks. And you might very correctly observed that in some cases, a natural language question is kind of overkill. For instance, what is translation from English to German? It's the exact same question for every single translation task that you want to trigger. Or, is the sentence positive or negative? It's really the same question every time for sentiment. But in half of the cases here, the question is actually different for each instance. So for instance, in question answering, you have a different question each time. For hypotheses and entailment, you actually include the original sentence, and we have, who's the illustrator of Cycle of the Werewolf. So you have different kinds of questions for semantic role labeling and relation extraction, for common sense reasoning, and for question answering, and so on. So half of the task, the question is different for every single instance, and for the other half, it's the same question just to trigger that task. But again, it would be nice if a normal person, and not a human, like expert and programmer, could trigger different kinds of tasks. All right, any questions so far about the task and the high-level ideas of everything is question answering? How did I decide T and what? So how did we decide like which tasks to include?
Like what does T look like? You say 0 is machine translation.
Oh, great. So what does T look like? So T is literally exactly this. So our task T definitions are just these natural words and natural sequences of words and sentences and questions. And that's how we encode each task. And we just let the model figure out how to actually deal with that. And it turns out the model is rarely ever confused about which task it's in based on these natural language triggers. There are some, for instance, like relation extraction and semantic role labeling that sometimes get a little bit confused with standard question answering because there's a lot of zero-shotness in all these three. But for the most part, the model is not confused if we just trigger it with the questions and in natural language as task definitions. Yeah, good question. Yeah.
How difficult it is to create a data set that take all those tasks to make you able to learn?
Great question. So how difficult is it to create a data set for all these tasks? Well, it turns out we will not create a new data set because that is a lot for the community to chew on. Instead, we will take the most well-established and reasonably sized data sets for each of the 10 tasks, and we just do a lot of different pre-processing. It's funny because when you realize, you think, oh, we'll just put them all together and it's a question, it's not that hard. But then you realize, man, each of the communities even has a different definition of what a word is. And so for instance, doesn't. In some data set, it's DOES space and apostrophe T. And so it's 2 words. And if you want to define, did you get the right span or not, it has to be both of those words together and not just one word. But another data set defines doesn't as just a single word. And so you realize, man, like the communities have really diverged and each of them has kind of worked on their own. And it's really hard to even unify them all with proper pre-processing scripts. So we thought it was very quickly, but it took us literally 3 months just to make sure all these different communities and tasks were formulated in a way that you can correctly identify and get the right metrics in the end for evaluating whether you're doing correctly or not. But yeah, we're not doing a new data set. We kind of have a metadata set that combines 10 existing ones. Yeah.
Why did you decide to use this high-level task compared to maybe tasks that require more fine-grained linguistic understanding?
Love that question. So why did we choose these high-level tasks like translation, summarization, so on, instead of more fine-grained tasks? I actually feel like if you make an argument that you shouldn't even tune your architecture for a particular subproblem in NLP, then also you probably shouldn't look at just these intermediate tasks because those, I think, are more and more likely to get learned as just part of model learning. So for instance, why did we not include named entity recognition or part of speech tagging in here, just knowing that's an adjective or verb? Well, one, those are, I think, relatively simple tasks. Nobody's excited about POS anymore. Like it's at 98, and it's been there for a long time, and maybe you get to 98.5 or something, or 99, but the world doesn't change that much with it. And I think these intermediate tasks are interesting if you're a linguist who wants to learn about language. But if you're an AI researcher or a practitioner, then really you just want to solve the task. And if you can do perfect in POS, but in the end your translation system still doesn't work, you didn't care about that intermediate task. And I think what deep learning has kind of shown us is that somewhat artificial separation into these intermediate tasks is not quite as necessary as we thought, and we can now do translation, for instance, without parsing, without NER, without POS, without any of these intermediate tasks. And if we can, and this is kind of, again, the difference, if you're a linguist, it's totally fine. If you want to just study language in order to understand language better, then it's great, and you can use this kind of framework to do any kind of tasks you want, like POS tagging, because maybe you want to understand how often different languages have adjectives before the verb or noun or after, right? And that's a totally legitimate thing to do. But if you are a practitioner, I think, of AI, and you want to get these tasks for real users to work better, then I don't think we have the necessity anymore to even work on these intermediate tasks, period. Like NER sometimes is still a little more useful because you can actually extract named entities in order to trigger certain things. Like if I see this company, then I want to do something, and I do automatic stock trading. So for instance, as a fun side note, very linguistic, in 2011, people realized that whenever Anne Hathaway started a movie, so Anne Hathaway, this very famous actress, she won some Oscars, and every time she started a movie, the movies got good reviews, the stock for the company Berkshire Hathaway, very different Hathaway, but same spelling, went up significantly. Every time she does a good movie, wins an Oscar, Berkshire Hathaway goes up. And so people know that there was already like algorithmic trading going on. People looked at the news and tried to very quickly trade on the news that was coming out. And in this case, we're doing entity disambiguation mistakes. And there, if you wanted to build the system and you really don't want to lose a bunch of money, you probably still want to use an NER system. But I think these, especially the first three, are probably the most interesting tasks of NLP, and they're the ones we're the least close to solving. But I also am questioning whether they need these intermediate representations that linguistics has done before. We could go, probably this is my first approximation to an answer, but I'd love to talk about it some more. All right, so basically now, as we're designing the system, we converged on everything is a question answering problem. Now, how do we solve this problem? Well, the simplest way would just be, you have a classifier in the beginning, you say, if translation, then run this translation model. If sentiment, then run this sentiment model. And of course, that's not what we're trying to do. If we did that, then there still would be no transfer between the tasks and no zero-shot capabilities of new tasks and any of that. And so we don't want to have any task-specific modules or parameters because we also want to not force the model to say, only use this skill to answer this kind of question. Maybe eventually we want to have combinations of skills and so on in the future. So we want to have the model be able to adjust internally to perform these separate tasks. And so all of that led us to this multitask question answering network for the data set that we define as DECA-NLP, the Natural Language Processing Decathlon. So 10 different tasks in one data set, the ones I just described, all cast as question answers, and we'll have a single model that essentially tries to give correct answers for all of these 10 different ones. And on a very high level, it's relatively simple. Namely, you start with some kind of context, some sequence model that goes over a context document. Then you ask a question. The question is also just a sequence of words. And then you generate one answer, one word at a time. And you can generate answer words through 3 different mechanisms, namely pointing to words in a context document, pointing to words in the question, or choosing a word from a standard softmax, like external vocabulary. And we'll learn some pointer switching mechanism that basically tells us which one to use when. All right, now I won't go into too many details of this model, but if you're somewhat familiar, and I know 2/3 of you are, and the other 2/3 maybe we'll chat a little bit afterwards, is most of these standard things that you've seen. In some ways, this reminds me a little bit of what Alex Krzyzewski did with convolutional neural network, where there's nothing really novel in there, but it's really tuning all the existing things that are out there really, really well and applying it in a new way, and then finding a couple of ways to actually make it work together. This entire code base is public. It has over 2,000 forks and stars and stuff on GitHub combined. And you can download it and run these experiments and get all the numbers that we mentioned here in the talk, and also apply it to any NLP tasks that you might want in practice. And it's kind of interesting. It seems like it has seen more uptake from practitioners rather than researchers, just because the task is still really, really hard. But we'll walk a little bit through this model now to give you a high-level understanding. So we start with the standard things, namely word vectors. They're still very useful, very important. We need to have some ability to know about words, even those we haven't seen in any of the 10 tasks. We also don't just have fixed clave embeddings, we also have character engram embeddings, so we can get a word representation for words we've never seen before in any of the data sets or in the unsupervised pre-training data set. We map those through a linear classifier and then put them into a shared bidirectional LSTM model with skip connections. And by shared, we mean that the same LSTM that goes through context words is also the one that will go over question words. Then we apply something called co-attention, which is essentially a fancy term for a lot of outer products between all the hidden states of those LSTMs. And that way, we get a representation of each of those two sequences that depends on the other sequence. So for instance, you might ask, well, why do we need to reinterpret the question based on the context? Well, if the question is, can I cut you? And the context is we're standing in line in a supermarket or in the market, then it's a very different context to you're holding a knife, right? And so you also want to reinterpret, you have the ability to reinterpret the questions given the context and vice versa. So now we have two sequences that are basically conditioned on each other. And then we plug both of those through transformer layers, the basic layer type of BERT and a lot of other popular models. Happy to go into more details later, but I probably don't have enough time right now. And you might ask, why not just use transformer layers everywhere? We've had a lot of success with that. Unfortunately, they're still very finicky, very hard to tune, and you might say, oh, transformers work great on this one task, but the learning rate has to be 0.001. And if the learning rate is not 0.001, it doesn't work at all in that task, and it needs to be 0.005 on, to make it work on this other task. And unfortunately, the transformer layers are not robust enough yet to be able to replace all the previous layers and co-attention and LSTMs. In fact, we had to, in the end, put again some LSTMs before and after the transformer layers to really make them robust enough across a bunch of different tasks. And then once we have now a basically sequence of all of these different words based on their conditioned on the entire context of both the question and the input document, we can now run a standard autoregressive decoder, which essentially is a classifier that at each point chooses between different attention mechanisms that might point to words in a context or points in the question, or choose an external vocabulary. So each of these will give us a distribution over potential output words, and in the end, we simply have a convex combination of each of these three different multinomials. Does that make sense? Any questions high level about this model? So a lot of the standard ingredients, LSTMs, glove, word vectors, transformer layers, and then a very simple convex combination of these pointer mechanisms, which intuitively are also just inner products between different words that you might see in the question in the context. All right, so now we have this model, we have the 10 tasks. Now how do we evaluate it? I mentioned there's some tricky issues with evaluation of a lot of these different kinds of data sets, and indeed each different subcommunity has defined its own metric. And if I want to put my really skeptical hat on, there are a lot of issues with most of these metrics. I'm actually going to argue, though, that you have less issues with all of them combined than you have with every single one. So the issues don't compound, but they actually alleviate itself. What do I mean by this? For instance, we've seen that machine translation is basically defined, how well you do machine translation is defined by this blue metric or blur metric, which is essentially a somewhat clever way of measuring how many n-grams overlap with your ground truth answer and your actual translation. And when sometimes you can translate the same sentence in different ways, but you probably want to have some kind of n-gram overlap to the ground truth. People have found that blue metrics don't necessarily correlate super well with human judgments. We've also noticed that Rouge, for instance, is another way to measure n-gram overlap essentially between a summary and a model, has a lot of issues and doesn't at all account for whether the summary is true or not. All right, and it seems kind of important for summarization to know it's actually a true summary, but if enough n-grams overlap, then you call it a success. So each of these have their own problems, but I think the problems get amplified when you have a community that just focuses on making that metric half a point or 1 point larger and then call it a successful paper. It's actually much, much harder to do that when you get evaluated on 10 tasks combined. And what we've noticed is it's really, really hard to get out of our thinking as researchers because we're so stuck, I think, as a community to be like, as an overall community, be like, well, this is the metric, I'm just going to fine-tune it. What we found is if we just look at the one blue metric and we fine-tune that, a lot of other metrics go down. And so you all of a sudden have to do model evaluations in a much more generalized way, and it's much harder to find sort of shortcuts of like, oh, if I just change the model a little bit here, I do beam search because I know from machine translation that works, that actually hurts somewhere else. And so it forces you to think much more broadly about all of NLP rather than each specific task. Now, you might argue, why didn't we just simplify it then and use a single metric? Well, we do want to be comparable to a lot of the other work that is out there on each of these tasks, and in some cases, it makes a lot of sense. So for instance, you don't want to use for a very unbalanced data set an accuracy metric or an exact match metric. You want to have some normalized F1 score and so on. And so we basically decided after a lot of back and forth and discussion to stick to each subcommunity's official evaluation metric. What's nice about all of these is, at least in theory, they all are between 0 and 100. And so what we're going to do is basically just sum them all up and say the new DECA score for these 10 tasks is the sum of how well you do on all of them. And as I've given this talk over the last 2 years or so, people say, oh, but it's ridiculous. Why don't you make Winograd schemas more important, because they really have this AI vibe and they're really much harder, and translation is just summary statistics and co-occurrence counts, and that doesn't really capture real reasoning. And then literally, and sometimes the same talk a few minutes later, somebody's like, but why don't you make machine translation more important? Because it's the much bigger data set, and who cares about those 100 pronouns in Winograd schema? So in the end, we decided all tasks are equally important. In theory, it should be easier to sort of say, okay, well, let's try to fix one task a little bit, but it's, you can't make the other tasks be hurting in terms of their performance too much as you're doing that. So now we're going to go over a bunch of numbers, but we'll dive into the details a little bit to unpack these relatively large tables. So here, what you see on everything on the left side is basically every single number comes from a different model. And here, every column, all the numbers of one column come from the exact same model with everything shared. All the word vectors, all the intermediate representations, including the decoder and the output layer. we'll basically observe a couple things. So one, sequence to sequence as a formalism by itself works reasonably well. You just kind of connect all these words and you try to generate it, but it is in many cases less performant than more advanced models, and in some cases pretty significantly so, like 10% worse, or squad much, much worse. Now we add self-attention, which is basically the transformer layers. We have co-attention, the outer products between things, and then we also add this idea that we have a question that is a separate type of sequence, and you can also point to its words. And that is basically the summary. So here, we want to look at the Decker score between these different models, and we definitely see the Decker score improving a lot. But let's dive into some more of the details. So the first thing is transformer layers and the self-attention really benefit a lot in both single task and multitask settings. So especially for question answering, where you want to point to a specific sequence, the transformer layers help significantly, like 20% increase in normalized F1 and exact match and things like that. Second observation, question answering and semantic role labeling actually have a surprisingly strong connection. This is especially because semantic role labeling, there are a lot of different semantic roles. We also see for zero-shot relation extraction, for instance, we have a huge increase. So zero-shot relation extraction is like there are new types of relations that you didn't see at training, and you still want to be able to identify, is this like a teacher-student relation, or a like seller-buyer relationship based on the sentence and things like that. We also see that pointing to a question is surprisingly essential for this overall model. What I want to also point out here is that even this is kind of amazing in the sense that these are the same architecture, just tuned on each task by itself. But that's also cool. We already have an architecture that works really, really well, and you can just tune it on any particular task. If you just care about that task, you can use that architecture even if you don't believe in multitask learning and combining all of these tasks. So that in itself is kind of incredible, that we found that we now have these kinds of architectures that work so well across tasks. So pointing to questions, surprisingly important. Surprising because even for things like sentiment analysis, which is just a simple classification problem, it was better to learn to point to the word positive and the word negative, which, by the way, also have their own word vectors, so class labels have some semantics already associated with them too, than just having a standard classification. And yeah, like I just said, multitask learning helps a lot in the zero-shot case. And that is kind of what I'm personally much more excited about, that you have almost a doubling in performance for a really hard zero-shot kind of task. But not all is great. So one, machine translation actually suffers a lot in the multitask framework. So you see here the second row, English to German translation got a lot worse. And that is largely because most of the other tasks learn to point to English words. And then you have this 10th task, which we wanted to include to make it hard, but maybe it made it too hard. Because now people are like, well, it's very easy to, if you're a translation reviewer, to say, well, this model is horrible. Nobody should ever read this paper. But there's some ways to fix it. But it's also clear that as you have these intermediate representations, all of which are in one language, if you now have one task only that now needs to generate a lot of German words, it's actually quite bad. And so that is one of the main reasons in the beginning of why the Decker score of a single model was worse than these 10 separate models if you were to have a system that perfectly could separate all the tasks. So this is kind of, we put it in parentheses because you need to have a perfect classifier. So as a question comes in, it needs to be perfectly classified into this is a zero-shot relation extraction task, or a squad task, or a translation task, and so on. And of course, translation versus sentiment you can do with 100% accuracy, but zero-shot relation extraction, semantic role labeling versus squad or question answering actually would make mistakes. So there is not a single sort of an oracle number that you were to sum it up, but it is still a number that we want to beat. And so we then looked into a lot of ways to improve the system, and one of them is actually on how do you optimize this. A lot of these tasks have very different sizes. So IWSLT for translation has hundreds of thousands of training samples, and window guard schemas only have a few hundred. And so this is another sort of unspoken issue in AI. Like if we have a system that has 10,000 training samples for one class and 100 for another, it just won't work. And nobody talks about that, and it's just kind of well accepted, and a lot of hacks, like we can weight the minority class a little bit larger with a little weight in our objective function. We can do some clever things in the optimization. And so we did all of this, and it turned out several of those officially well accepted hacks didn't quite work. So the first idea was we do fully joint training, which worked surprisingly well, where we just go through all the different tasks, and then each mini batch we basically take from one particular data set. Then we thought, well, there's this whole paper that has 1,000+ citations on curriculum learning. So maybe what we should do is we start with simple problems, and then we get successively harder and add more and more of the harder problems. And it turned out that was the opposite of what you should be doing. And intuitively, it kind of makes sense. If you make this whole complex model of all the transformer layers and LSTMs, and then you train it first all the way to do really well in sentiment classification, which is probably the simplest task of all of the 10, then it'll just get really, really good and make all of its parameters good at saying positive, negative. And that's it. And we'll do nothing else. And if you then say, all right, JK, now not just positive, negative, but all German words and all squad phrases, and it's really hard to get out of that local optimum that it's now stuck in with all of its weights. And so what you actually want to do is the opposite, namely what we call anti-curriculum pre-training, where you actually start with the hardest tasks, you force the model to stay quite general in all the parameters and be able to generate a lot of different kinds of outputs, and then you just add sentiment in the last couple of iterations after you've done working on the really hard tasks. So with this anti-curriculum strategy, we made a big jump in DECA score, and then we started tuning a bunch more on basically trying to close this gap. What's interesting is sometimes with certain things like anti-curriculum, we dropped the gap, but sometimes we had improvements like even better word vectors, like Cove instead of glove, and so on. And then we're excited because our DECA score for the single model got better, but then also all the single tasks got also better, and the gap actually increased, and that wasn't, we're not as excited about the single task improvements, but want to keep it real. So of course we ran all the improvements we made on the single multitask model, also on all the single task models, and so everything improved. So that's great also. But the gap got larger again. So then we started thinking more about this anti-curriculum strategy and included more of the harder tasks into that first phase of training, and then basically dropped, that basically helped us drop the gap to about 5 points. And then we realized, well, translation is still not doing as well, so we started oversampling, and just inside each of all the iterations, we just kept oversampling the translation task and put more of those training samples in more of the mini batches, and that helped us drop the gap to a little less, around 1 point. And so basically now, statistically significantly speaking, we're pretty much the same. So we're able to train a single model to do as well on 10 different tasks than 10 separate models, which I think is pretty exciting. Now, a little bit of analysis and some sort of outlook on what this might lead to. And I think this is focused on NLP, but I think it's a very general idea that we're describing here, maybe multitask learning. And I think it can apply and has been applied to a lot of interesting combinations of tasks in computer vision and so on. The default papers you will see usually will only include the tasks that we know will work better for by combining them. So for instance, we know that part of speech tagging helps named entity recognition. So if we do multitask learning on those two, we'll get a better number and we can publish a paper more easily. Here, we made the maybe mistake of including some really hard tasks that are absolutely not helping each other and say, well, this is an interesting challenge, like we need to figure out catastrophic interference and forgetting. It's a really interesting problem, I think, and something to publish, I think, a lot of exciting papers in the future. And namely, if you train on one task and you then train on a second, you usually start forgetting the first. So this is catastrophic forgetting in sequential learning. And when you can still go back to the different tasks, we call it catastrophic interference, because as you're training translation, your other abilities like question answering usually get worse. And so I think this is one of the big open problems in AI research in the next years to come. Now, what surprisingly wasn't a problem for this model is knowing how to answer the different kinds of questions given this natural language sequence as questions. And so here we see, for instance, squad, almost all the words come indeed from the context pointer, and there are a few where it's actually able to just classify it with a standard softmax. And IWCLT, the translation task, for the most part, you don't have the words in the context, so it generated them from an external vocabulary. But of course, there you might have personal, concrete nouns like Richard or Kenya, and then you can just kind of point to the original context in the original language, and that works too. So basically, answers are mostly correctly copied from the right places, the context or the question, and that there's no confusion in the model about that. Now, what I was very excited to see is that pre-training on Deka NLP somewhat helps also in the final performance on other tasks. So here we took a full model as it is, not just the word vectors, but everything including the decoder, and we basically train it on a new task. So we have a Deka pre-trained model versus a randomly initialized architecture of the same kind. Actually not fully randomly initialized, we still have word vectors at least to make it a more fair comparison, but we basically train it on named entity recognition or on a completely different language pair like English to Czech translation, and the pre-trained model just added a new task to the code, rerun the model will essentially give us, in the end, a higher performance overall in terms of blue score and exact match. What's even more exciting is the model seemed to also do zero-shot domain adaptation very well. Namely, we had trained it on movie reviews, but we, out of the box, with no extra training, achieved 80% accuracy also on Amazon product and Yelp restaurant reviews. So domain adaptation is much, much simpler with this model. We also trained it on another natural language inference task, an entailment here, SNLI, where out of the box it achieves 62 without any additional training. But if you then fine-tune it, it'll get, of course, a lot better on that data set, and then also is better than having a model that was randomly initialized. Now, this part is sort of the most exciting, I think, and we have seen sort of more quantitative ways of seeing this, or observing this in the zero-shot relation extraction numbers. But here we came up with our own examples of trying to make the model classify something it's never seen before. And basically, we came up with some simple stories like John had a party, but no one came and he was all alone. And we asked, is the story sad or happy? And the model could now do all kinds of things, right? It's never seen this kind of question before. It could just throw out some random German words or whatnot. But it actually learned to point to an answer, to a question word, and it, in more cases than not, actually points to the right adjective of this question. And this doesn't always happen, and you can, there are lots of adversarial examples, so we're not claiming we solved all kinds of questions, but it's kind of amazing that it works, given all the possible things it could be doing, that it actually points to the right kind of adjectives, and in even some cases at all, is kind of amazing. The random baseline here is extremely low. And so I'm more excited about that kind of capability than like another 2% Blue Point improvements after tuning and adding a bunch more data to a particular task. And I think there's a lot of interesting things that we can evaluate and explore in this direction and kind of generalize AI system past exactly so the convex hull of things that they've been trained on. All right, so hopefully I could encourage some of you to think about this kind of line of research. I think it's a super interesting new framework, thinking about multitask learning and unifying different AI tasks. It helps us with more general language understanding, multitask learning in and of itself, of course, domain adaptation into different domains, transfer learning. We can actually study how well could output layers transfer also, not just word vectors. We can pre-train more and more layers of these models and hopefully eventually be able to do zero-shot learning a lot more accurately. And with that, there's a ton of related work. In a better, like, sort of very scientific talk, I would have had like hundreds of citations. In fact, that conference submission length paper has, I think, 10, 12 pages of citations, because as we're combining all these different communities and different data sets and different models and so on, there's a ton of related work. These were some of the ones that influenced us the most in thinking. Colbert and Weston was the first to have a neural network NLP paper, not an NLP conference, but at least an ICML for a unified architecture for NLP. But of course, the NLP tasks back then didn't include the really hard ones like summarization, translation, and things like that. But it's still sort of a very influential paper, I think, and it's a great read for all of you. And then, interesting models that have come out that also included various pointer mechanisms and so on, and evaluation of those pointers here by Abigail C. and Chris Manning. So, what's next for NLP, and I think for a lot of other AI areas, is really trying to come up with more general models that can do multiple things at once. And with that, thank you. And I think we have time for a few questions.
Thank you very much for that. I've got two questions. The first one, I saw the results for where you're comparing the same model of the two ways of doing it. Where English to German translation never did well. Is it right to assume that this is highly biased to English, and if you try it the same on other languages, it will flop? And then the second question is, I've seen your example on question answer. How was the performance on the dialogue?
On what?
On dialogue.
So the dialogue state tracking here is on, where is it? So we have, I guess I don't have my laptop, I can't switch to different ones. I think it's this data set here, dialogue state tracking, so it's doing quite well. And how focused is it on just English? I think this model is so general, it can work on any language. It really just assumes a sequence of characters or words in a context document or a question, and you can make it more robust if you added more languages of other kinds to it. Even just the way we got from a pretty horrible blue score here in translation to like almost double was just by oversampling more of that data set. So if you wanted to translate to Swahili or German or French or something, there's no reason why this model would not work. I mean, it has the same issues that all other deep learning models have, which are actually quite interesting. So other interesting research questions for deep learning and NLP is numbers. It's kind of crazy, right? We represent even words like love or person as a list of numbers, but when it comes to actual numbers like 3, we also map the single integer 3 to a list of 500 floating point numbers. And then we can't do reasoning as well anymore as we could originally. So this idea that numbers are a big problem for translation and summarization, especially for this model as it is for all deep learning models. Another one is words of people names. So John, Jason, Jeremy all have a similar word vector, but in the summary is really important if Jeremy got, murdered or something, or won the Oscar versus Jason winning an Oscar or something, right? And so, but for summaries, they just look at similarities in word vectors, and then they will often become factually incorrect because they generate the wrong word vector of a different first name. But those problems are kind of general for all deep learning NLP models.
So obviously you chose English to German, which was one of the harder choices you could have made. Have you tried just adding in English to French and maybe another language and see if you can just give me more context on languages? Because right now obviously all these tasks are English except for we've got German.
Right.
So even translating what are the data sets and just kind of giving more context about like languages in general. Because I suppose that's why you have to do that.
It's a great question. Yes and no. So we wanted to keep the hardness, but then we started doing some follow-up papers where we just had simpler tasks that don't include, for instance, translation, and then all the things get a lot easier and better. And I'll talk about some of that more recent work in the NLP session. But we did actually include another run where we had 20 more translation pairs between like a bunch of different languages, and it was like a 30-task single model. And it kind of surprisingly just continued to work. Like, we didn't immediately hit like a huge drop-off after like 5 more language pairs, and then things got really horrible. In fact, translation overall improved. But of course, like, the other tasks didn't like get a lot better, and they kind of wiggled slowly into the decay as we added more and more just translation pairs.
So I appreciate like the approach you're taking where you're trying to transfer from task to task and not just intermediate representations. But have you tried looking at the word vectors you get out of a model trained like this? Because the word vectors would be useful for many different tasks. So have you tried looking at those? Or is there a significant improvement over like single task language modeling, learn word vectors?
Sorry, what's the question? If word vectors improved? Or?
Yeah, so if you can get word vectors out of the multitask learn model.
Oh, that's an interesting question. We didn't try that. So you're thinking about maybe taking the final representations of the model somewhere right around here? Like thinking about these as your contextual word vectors and then seeing if they worked on other tasks? Is that the question?
Yeah, something like that.
So in some ways we did, in the sense that we applied it to named entity recognition and different domain adaptation, sentiment tasks, and so on, and just immediately looked at whether they worked or not. But the nice thing is we didn't have to. We could have made our lives even easier and say, yeah, sure, we just take this, and now we retrain the last part again. But that is kind of what everybody else is doing with all their word vectors. But you're right, that might be a simpler thing to do well on. And should probably be evaluated. That's a great idea. That might be now easier to actually get a paper out than the original one. Yeah, it's true. And it's kind of incredible, but papers are, and I keep thinking about this, like such an economic, like amazing opportunity. Like if you have a good, strong NLP paper at ACL, EMLP, or an ICLR, ICML kind of paper, like, your income just like doubles, even in Silicon Valley. So from here, it might like 10x, 20x. It's incredible. So I think there are a lot of interesting like opportunities for papers, and you definitely just mentioned one. That's cool. Yeah.
Good morning. I'm James. I'd like to know, is there a reason why you didn't include some image-related tasks, like for example VQA, because maybe try to also measure the performance on multimodal data might be useful. Try to incorporate information from visual context might be useful. So is there a reason why you did not include a VQA task?
Great question. So why did we not include visual question answering? We actually talked about it a lot. There was a lot of back and forth, and people are like, oh, why not add one? But then some arguments for why we have not yet. It's definitely a very reasonable thing to do in the future. One, I didn't want to have a separate, like, if we also have images, then add this other mechanism to it. I wanted to have a single model for everything. And then we realized there's still so many problems in just all the NLP tasks to be unified that it felt like a little too early to also include yet another modality. I was like, Brian said, oh, let's just throw that in there too. And I'm like, well, let's just solve this one a little bit more so that we actually get state-of-the-art numbers on more tasks and so on, rather than adding like an 11th one in. Because then at some point it becomes a little much, and it becomes more and more of an engineering challenge also, and it's harder and harder to think like, how do we actually optimize in this multitask setting and so on. But it's definitely something that this, I feel like, should help, as in when you know about entailment, it would definitely help in doing visual question answering better, right? Because you know that 5 people playing soccer is logically entailed in 10 people playing soccer. Like, you need to have 5 at least to get to 10. And so I would assume that this model kind of benefits in that transfer learning setting for VQA too.
Sorry,
Yep.
I asked this disclaimer that I know very little about NLP. What is the structure of your vocabulary reference? And is there a lot of opportunity to include some sort of semantic knowledge representation in this multitask learning setting?
So in some sense, the best approximation to semantics that we have in the meaning of words is just these word vectors. And they essentially just capture co-occurrence statistics, which sounds kind of lame, but it's a really, really powerful idea that, all of these, glove and word-to-vec word vector representations came from, and it works surprisingly well. So I'm sure most of you are familiar with this if you're in NLP, but for instance, if you take the word vector of, and this is probably the single best example, a lot of others aren't as exciting, but if you take the word vector of king and you subtract the word vector of man and you add the word vector of woman, you get to somewhere into the vicinity of the word vector of queen. And so there are actually a lot of semantics that are captured just through those co-occurrence statistics. And where you run into problems is with antonyms, for instance. So good and bad, actually, with just co-occurrence statistics, are relatively similar to one another, because this movie was good. I thought the talk was good. Like, I had a good day. All of these, you could have put bad in there too, and it's not an unreasonable sentence also. So antonyms often get similar word vectors, and then country names get similar word vectors, and people names get similar word vectors. And so even though they're, in very many cases, like very, very different kinds of people. So there are issues with it, but that is kind of the best approximation to semantics that we currently have. You can also infuse ontologies into these by backpropagating and trying to complete a knowledge base. So if you know, for instance, Obama is president of the United States or something, you can have an ontology, and basically each node in the graph is a word vector also, and then you can backpropagate facts about those word vectors into them, and then the lists of numbers that represent each word kind of start to capture some of the facts of that knowledge base as well. So there are a lot of ways you can kind of infuse semantics in backpropagatable kind of word vectors. Yeah. We could have, and I have done lots of long lectures on just semantics. There's a lot to it, but yeah, that's kind of our best approximation right now.
Hi, thanks for the talk. So on these multiple tasks, multitask setting, I guess you're hoping that somehow you learn powerful intermediate representation to perform these tasks. Is there evidence from looking at applications that that's what's occurring? For example, have multiple lottery networks that maybe activate each task separately?
So we looked a little bit at the activations across different tasks, and indeed there are certain neurons that activate more frequently for specific tasks. So that is kind of the best that we've seen so far. It is hard, as you go deep into the middle of the second or the first transformer layer after all these other things, there isn't a very obvious pattern a lot of times to oh, this is obviously now a translation task given the previous things or something like that. But the higher up you go, the more distinct the activations become for the different tasks. I think there's one up here.
Okay, hi. did you consider using ensemble methods, or was there benefit in having all the data trained through the same model?
We have not done an ensemble yet. I think that in my eyes, like, ensembles are often a good way to get to that last spot on the leaderboard. If there's a lot of competition and all the ideas are sort of out there and you try to squeeze out another 1 or 2%. But I think originally when you're just starting out on a new research problem, it's probably not the first thing I would jump to. And this is kind of all very early days still to try to create a single model to do something really useful. So my hunch is, for sure, if you train an ensemble model, especially with the various different optimization strategies that we had to come up with over the course, like all these different kinds of training strategies, and then you ensemble that, very likely you'll do better. So it's a reasonable thing, but you have to also acknowledge that these models are already quite large, so then having to run an ensemble of a bunch of really large models will just slow you down quite a bit. And I think research-wise, it's more interesting to try to get that single model to do more and more things more accurately still. Yeah. But it's definitely a reasonable way to squeeze out a couple of percentages. All right, awesome. Thanks everybody for your attention. Thank you.
First one is that all Nigerians, you are asked to take a picture with the winner of the Maathai Award right outside this room. And the second announcement is that we will have a break from 10:30 to 11, but that the coffee and the snacks are delayed a little bit.
Sure.
And yeah, for the rest of the day, there will be parallel sessions on natural language processing, mostly ML in production, startups, and innovation. And later, you will have talks.